We turn our attention now to using the chain rule to understand a little more about implicit differentiation. We have a setup here. Let f of xy equals 0 be an equation that defines y implicitly as a function of x. But if f of xy equals 0, then what is there to talk about? No, what this means is, if you think back to first semester calculus, you saw equations like x squared y plus xy squared, say minus 3 is equal to 0, and you implicitly differentiated to find y prime. What we're saying is, well, now we're going to say that the expression, the x squared y plus xy squared minus 3, is a function of x and y. And if we had an equation to begin with that wasn't equal to 0, we would move everything to one side and let it equal 0, and that's what we're talking about. It's almost kind of like a level curve for the function f of xy, where the value of k is equal to 0. Anyway, that's what we're talking about here, an equation that defines y implicitly as a function of x. Then we can use the chain rule to find the derivative of y with respect to x, and it's going to look like the partial of f with respect to x times dx dx plus the partial of f with respect to y times dy dx is equal to 0. Now, folks, dx dx is equal to 1. And if we rearrange this equation, we can conclude that dy dx is equal to the negative of the partial of f with respect to x divided by the partial of f with respect to y. We can rewrite that as dy dx is equal to negative fx divided by fy, provided that the denominator fy is not equal to 0. We can extend this to more variables. Let f of x, y, z be an equation. It would help if I wrote an equation, wouldn't it? Let f of x, y, z equals 0 be an equation that defines z now implicitly as a function of x and y. Then, using the chain rule again to differentiate with respect to x is going to give us the partial of f with respect to x times the partial of x with respect to x plus the partial of f with respect to y times the partial of y with respect to x plus the partial of f with respect to z times the partial of z with respect to x is equal to 0. And you can see that I'm using the subscript notation for the partials of f. As before, the partial of x with respect to x is equal to 1. The partial of y with respect to x, well, folks, as far as x is concerned, a partial derivative is holding y constant, and so the partial of y with respect to x is 0. Therefore, the partial of z with respect to x is equal to negative partial of f with respect to x divided by partial of f with respect to z. Similarly, the partial of z with respect to y is equal to the negative partial of f with respect to y divided by the partial of f with respect to z. I put a period, I need to put a comma, provided that the partial of f with respect to z is not equal to 0. I'll put a box around both of these results. Let's see an example of this. Find the partial of z with respect to x and the partial of z with respect to y for x squared minus y squared plus z squared minus 2z is equal to 4. And we're going to use these expressions that we just wrote down for these partial derivatives. We may know right away that this equation doesn't have a 0 on one side, and we want to have a 0 on the right-hand side, or on some side. We actually don't care if it's on the right-hand side or the left-hand side, do we? Anyway, that means that we're looking at x squared minus y squared plus z squared minus 2z minus 4 is equal to 0. Well, folks, we need the partial of f with respect to x, the partial of f with respect to y, the partial of f with respect to z, and to put them together. So, pause the video and do it. Come back when you're done. Right about now, you're probably thinking, please put this on the test, right? Anyway, partial of f with respect to x is going to be 2x. With respect to y is going to be negative 2y. And with respect to z is 2z minus 2. Using the expressions that we have, negative partial with respect to x divided by partial with respect to z, we get that the partial of z with respect to x is equal to the negative of 2x divided by 2z minus 2. Dividing out the 2's and then applying the negative to the denominator, we get that the partial of z with respect to x is x over 1 minus z. Likewise, partial of z with respect to y is the negative of negative 2y divided by 2z minus 2. Dividing out the 2's and letting the negatives offset each other, we get that the partial of z with respect to y is equal to y over z minus 1.